Hello and welcome to Lecture 9 of our Natural Disasters course. In this lecture, we'll be discussing severe weather, such as tornadoes, lightning, heat, and cold. So with regard to severe weather, it causes about 75% of the yearly deaths and damage from natural disasters. So severe weather is by far, on a cumulative scale, the most deadly type of natural disasters. So more people are killed usually by severe weather than by earthquakes, volcanoes, and mass movements, landslides combined. And from the time period of 1980 to 2009, the U.S. had 96 weather-related disasters, causing more than $1 billion each in damage. They total more than $700 billion between those 96 events. So severe weather, though they're not always large in magnitude, they're very frequent, and because they're very frequent, they kill small amounts of people, but it adds up. So deaths due to severe weather in the United States from the time period of 1977 to 2011. See, the event is on the left-hand column, and the average yearly deaths is on the right. Interestingly, heat is the most lethal form of severe weather, followed by winter storms and cold, and floods, tornadoes, hurricanes, and lightning. You might be surprised by heat being the most lethal form of severe weather, but most people don't realize that heat is not as apparent as a threat, and so people are less likely to take measures to mitigate the impact of heat. And as we'll learn, most people that are casualties of heat are older and younger, older people, and then very young children in areas where they don't have access to cooling. And so the more dramatic events, such as floods, tornadoes, hurricanes, and lightning, people tend to take more measures to avoid them, and they're also not as frequent as heat. And so this map of the United States shows the number of events in a given year of severe weather. So basically thunderstorms, severe storms, tropical storms or hurricanes, heat wave or droughts, floods, wildfires, winter storms, or freezes. So these are the different types of severe weather events. Here we have the number of events, the percent frequency, normalized damage, billions of dollars, and the percent damage. You can see where the most severe weather occurs in the United States is in the south central and the southeastern part of the country. Now, why is that? Well, we'll discuss that moving forward. It has to do with its proximity to basically the Gulf of Mexico. So the first form of severe weather in particular we're going to discuss is cold. So a case example, there was a long period of extreme cold in Central Eastern Europe during the 2012-2013 winter. Over 600 people perished. And so this high death toll was not necessarily due to the extreme weather per se, but rather a lack of infrastructure in the former Soviet bloc. So these countries in Eastern Europe are former Soviet countries, and so after the Soviet Union fell, their countries were left in somewhat political, economic turmoil, and so they didn't have the infrastructure to handle the severe cold and the snow. So many people were snowed in; they couldn't get out of their houses, and they eventually ran out of food and heating oil. And so that's unfortunately how a lot of people perished. And here, see, this is the temperature departures between January 25th and February 14th. So you can see there's negative 20 degrees Fahrenheit below average temperatures in some places, negative 15 over this large swath. And so it was a change in the jet stream that brought this about. So usually the jet stream, it flows this way, so we have cool and dry air, but it's not that cold. It's not the polar air, but the jet stream took this jog up and then came down, dipped down deeper, which allowed for this much cooler polar air to descend down over Central Europe. And so that was a devastating event. I don't know if any of you remember that. I remember hearing reports of it. And so another risk associated with cold is frostbite. So frostbite is whenever your tissue freezes, whenever water freezes, it expands. So if the water in a cell freezes, it expands and it ruptures your cell membrane and it kills your cell. So if ever your tissue freezes, it's dead. It doesn't recover. So frostbite is very dangerous. If you have frostbitten toes or fingers or the tip of your nose or your ears, they have to remove that dead tissue. And so frostbite is not only a function of the temperature, but also the wind, because the faster the wind is, the quicker heat is removed. Because if you're just standing in a region where there's no wind, as your body radiates heat, it warms the air around you, and the warmer the air is around you, basically the less temperature difference there is between your body and the surrounding air, and so heat will flow more slowly. The larger the temperature difference, faster heat flows. So if there's wind blowing, constantly removing the heat that's coming out of your body, and instead of bringing in new cold air, then that temperature difference always remains high, and so heat flows out of your body at a higher rate. And so these are frostbite times. That's what these. So this is the temperature. So it's 40 degrees Fahrenheit, negative 45 degrees Fahrenheit, and this is the wind speed, 5 miles per hour to 60 miles per hour. And these are the frostbite times, these colors. And the number is the wind chill, right? So that's what it feels like. That's what the temperature feels like. So here it takes 30 minutes to get frostbite. Here, 30 minutes here, 10 minutes here, and 5 minutes here. So it can be relatively warm. So like a 5 degrees Fahrenheit, it's not that crazily cold, but if it's a 60 mile per hour wind, you can get frostbite in 30 minutes. Right, so frostbite is definitely something to be aware of. Now we're going to look at some winter storms. So the eastern United States had the storm of the century, what's known as, in 1993. So an immense cyclone covered the area from Cuba to Canada. It transversed that area. It didn't cover that whole area at one time. Between March 12th and 15th, it killed 270 people and caused more than $8 billion in damage. So there was a large dip in the jet stream that caused the collision of 3 air masses over Florida. So we had low pressure, warm, moist air from the Gulf of Mexico to the south of Florida, fast moving frigid Arctic air from the north coming down from Canada, and then rainy, snowy east moving air coming from the Pacific. All 3 of those air masses combined over Florida to create fronts. And anytime we have fronts that combine, that's the recipe for storms. And then once these storms develop, they just rode the jet stream up the coast. So this is where the storm developed, and you can see how it moved up the coast. This is the radar, the echo soundings through the radar. So speaking of radar, Doppler radar has helped us mitigate death at least due to severe weather significantly. So how Doppler radar works is it uses the Doppler effect, and that when you send out a radio wave, that radio wave will bounce off of objects and return to where it was sent. And if that object, either the object it bounced off of is moving, or the source that transmitted the radio wave and then it records the echo is moving, then the frequency of the radio wave will be shifted. Right, so in most cases, the source is stationary, and you send a radio wave out, it bounces off of something and comes back. If it's moving away from you, the frequency comes back lower. If it's moving towards you, the frequency comes back higher. And By measuring that shift in frequency, you can actually measure how fast the object the radio wave bounced off of is moving. If it shifts a lot, if it shift a lot lower, then that means the object is moving fast away from you. If it shifted a lot but it's higher, that means the object is moving fast toward you. This is how radar guns work for police officers, how they measure your speed in the car. They shoot radio waves out at your car, which bounce off your car and come back to the gun. They can measure how fast your car is traveling. This is how they measure velocities in sports, which is how fast the pitcher threw was traveling. This is also how we track precipitation in the atmosphere. So we send out radio waves into the atmosphere, and if there's any precipitation, such as rain droplets or snowflakes or ice crystals in the atmosphere, they reflect the radio waves back. Now, if the frequency of those radio waves is shifted, then that means that that precipitation is moving. And we can measure how fast it's moving and in which direction. So Doppler radar was a significant advancement and allows us to track the motion, not only the intensity, how much precipitation there is, but the motion of the storm. So radar detects precipitation, as I said, by using reflection of microwaves and radio waves. They're similar in frequency. The reflectivity increases as the precipitation increases. And this technology allows us life-saving advanced warnings for storms. You can see what trajectory they're moving on and can evacuate people. So a blizzard is a strong cyclone with winds of at least 60 km/h and below freezing temperatures. There's either blowing or falling snow. And so the cyclone itself, the storm system itself, might be traveling very slowly, although the winds of the cyclone are very fast. Those are actually the worst kind because they drop a lot of snow whenever they're traveling very slowly. So in the northeastern United States, between January 6th and 8th, 1996, there was a Canadian blizzard that dropped record snowfall in Ohio, Pennsylvania, West Virginia, and New Jersey. Wind speeds exceeded 80 km/h and it killed 154 people. I remember that storm. I lived in Pennsylvania at the time, and I was, I think, 8 years old. Nope, 10 years old. And I remember the snow was so deep, it was between like my waist and my chest. It was extremely, almost up to my chest as a 10-year-old. It was very, very deep snow. I had a hard time getting out of our house. And this was followed by immediately warm weather and heavy rains, which caused destructive flooding as all that snow melts, created large amounts of runoff, resulting in flooding. Then we have ice storms. So precipitation, it falls as snowflakes or ice particles in the upper atmosphere. And as it travels down through the atmosphere, it enters warm air, which causes it to melt into rain. And then in most cases, the rain just falls and hits the ground. However, if it's cold, because remember, the upper atmosphere is always very cold. That's why the precipitation at high altitude is always ice or snow. It's only whenever it falls down closer to the surface that it melts into rain. However, if there is a layer of air that on near the ground that's cold, say it's in the wintertime, the rain then enters that below freezing layer of air near the ground and it refreezes into sleet. So that's how we get sleet. That's also how we get snow. Snow is never, it freezes again into snow, but it's just it's all about the time scale of how fast it happens. So if rain is not below, if the rain is not in the below freezing layer long enough to refreeze, becomes super cold, and then it freezes as soon as it comes in contact with the ground or a solid object. And that allows coats of ice to form on objects. That's when you have those significant ice storms where you just see like just coats of ice and everything. That's what they often call as freezing rain. So the rain falls and then it freezes on impact. So in general, we have precipitation falls as snow, and as it enters the warmer air, it melts and falls as rain. If the whole air column is cold, say in the winter, it always stays as snow, and it falls to the ground as snow. However, if there's a very thin layer of below freezing air, Then as the snow falls, it melts, becomes rain, and it enters this small area of below freezing air. It forms freezing rain, where it hits and then freezes upon impact. If the cold air layer is larger, then the rain actually freezes into sleet, so little ice particles before it hits the ground. So an example is the Canadian ice storm in 1998, in early January. There was 80 hours of freezing rain. 25 people died from hypothermia, and there was $7 billion in damage. The power system collapsed under the immense, it was under immense damage and had to be rebuilt. So all the ice accumulated on the transmission towers, and the weight of the ice caused the transmission towers to collapse. And so the electrical grid was significantly damaged. This is a picture from St. Bruno, Quebec. So then we have the lake effect snow. If anyone's from northwestern Pennsylvania or western New York, or parts of Michigan, you know what lake effect snow is. It's common along the eastern shores of the Great Lakes. What happens is cold air moves over the warm waters of the lake, and the air obtains moisture from the lake. And then over the air that moves over the cooler land, the moisture condenses and precipitates out as snow. So this is most likely to occur in the late fall and early winter. It also occurs elsewhere around the world. But so as this air moves over the lakes, it accumulates on this moisture, and as it moves over the land, it cools over the cooler land, and then all that moisture falls out as precipitation in the form of snow. You can see how the wind's blowing. It's picking up the moisture over the lake, and as it comes over the lake, you can see the clouds forming and it's dropping snow. So that's the lake effect snow. It happens on the eastern coast because we have the westerly winds, the winds that blow from west to east. And so there's a cool picture of the lake effect snow there. And here's another example of lake effect snow. This is the seasonal snowfall for forecast for 2004-2005. You can see this is over 100 inches in parts of New York, right from this lake effect snow. And you can see we have significant snowfall in this region because of the location relative to the lakes. So now we're going to talk about thunderstorms. And so the air temperature, as we said in our last lecture, it normally decreases as you go upward from the surface. We said for dry air, it's about 10 degrees centigrade per kilometer. But for moist air, it's about 6 degrees centigrade per kilometer. And if this lapse rate, if this rate of cooling is any greater than 6 to 10, the moist and the dry lapse rate, then the atmosphere is unstable. And that rising warm moist air may begin condensation, releasing what's called the latent heat of vaporization. So that's the heat that's in the water vapor that was required to vaporize the water. Whenever that water vapor condenses out, it releases that heat. And that heat, when it's released in the atmosphere, it provides energy for the severe weather. How does it provide energy? Well, it's heat that warms the atmosphere. And as the atmosphere becomes warmer, it becomes less dense. And because it's less dense, it wants to rise with more vigor. And so the updrafts become stronger and stronger as more and more energy in the form of this latent heat of vaporization is brought in. And so as those updrafts become stronger, the pressure drops because you have air moving upward faster and faster. In order to replace that air that's moving upward, air from the surface has to move in. So the wind speed along the surface increases. So you have this positive feedback loop that as long as you have moist air, water vapor that's being brought into the storm will continue to intensify. So here is a warm, humid air that updrafts. As it moves up, it adiabatically cools. The water vapor begins to condense out and precipitate. and then the precipitation comes down, and that brings cooler upper atmosphere air down with it. And eventually these cool downdrafts will spread out, and they'll disrupt the warm, humid updrafts and basically choke the storm of its source of energy. Now, this is called an air mass thunderstorm, or a single cell thunderstorm. This is the type of thunderstorm you experience on the afternoon of a warm, sunny day. You know, in the summer, how there might just be all of a sudden a thunderstorm. Well, what happens is, all throughout the day, the air along the surface is becoming warmer and warmer and warmer, more and more humid. To eventually, it has such a low density that it begins to rise all of a sudden. And as it rises, all that water vapor condenses out, and you have this thunderstorm. And then as the rain brings those downdrafts with it, they cut off the source of energy, that updrafts, the warm, moist updrafts. That's why after a thunderstorm, it's always a little bit cooler. If you ever notice, it's cooler because now those downdrafts have come from the upper atmosphere to shut the storm down. So this is a single cell or air mass thunderstorm. They're relatively short-lived, and they're not that destructive. So the early stage requires a continuous supply of rising warm, moist air to keep the updraft and cloud mass growing. The mature stage is the upper-level precipitation begins when ice crystals and water drops become too heavy for the updraft to support. And so the falling rain causes downdrafts, pulling the cooler, drier air down with it. The updrafts and downdrafts blow side by side, creating gusty winds, heavy rain, thunder, and lightning. And then finally, the dissipating stage, the downdrafts drag so much cool, dry air that the updrafts necessary to fuel the storm are cut off. So the other type of thunderstorm is called a frontal cyclone. So these are not short-lived, and they are moving with a front, and so they don't get shut off. Their supply of warm, humid air is more continuous, so they can escalate into much more intense storms. So we talked our last lecture how we have a front, we have a low pressure normally along that front. Air begins to rotate in towards it, we create a cyclone, and the front separates into a warm front and a cold front. And in the warm front, remember a front, warm front is a front behind which warm air is advancing. A cold front is a front in which cold air is advancing. At the warm front, the warm humid air rises gradually up over the cold air, and so you have a gradual cooling and condensing of the water vapor. And so the energy, latent heat of vaporization in the water vapor, it's released over a distributed area, so you don't have intense localized storms. Whereas the cold front, the warm moist air is pushed up more dramatically, so you have that water vapor condensing out, releasing the latent heat of vaporization in a localized area. So you have very localized release of energy, and so you have the formation of some significant storms. So you can see in this cyclone, this is the cold front right here. You can see that edge, that's the cold front where this massive cloud mass is. That's where the warm air is being pushed up by the cold air, and it's all condensing out, causing severe storms. So these frontal cyclones, these are the most dangerous type of thunderstorms. In the northern hemisphere, the cyclone rotates counterclockwise, and the air mass rotates around a low pressure core. On a large scale, the trough in the jet stream juxtaposes the northern cold front with the southern warm front. And so the jet stream kind of acts as the barrier between the cold polar air and the warmer, moister air of lower latitude. And so it's along these jet streams that usually these frontal cyclones form. And then the storm just follows along with the jet stream. It tracks along the jet stream. And so it forms a line of thunderstorms along the cold front that just tracks along the jet stream. And so in northeastern U.S., low pressure system moving up the Atlantic coast, it draws northern cold air, moisture from the east, and that's what we call nor'easter. So a storm that travels up this way. If the jet stream takes a dip like this, and a storm traveling up this way is bringing in cold, dry air from this side and moisture from the Atlantic. And that moisture, that water vapor, that's the source of energy. It tracks along the jet stream up here. That's what we call nor'easter. So on a medium scale, we can have individual thunderstorms, and on a small scale, from these thunderstorms can spin off tornadoes, which we'll talk more about in a little bit. So comparing air mass versus severe thunderstorms, air mass thunderstorms, they're the most common type of thunderstorm. They're a result of small scale convection in the atmosphere. They're common in low latitude, like the tropics all year round, but they're common at the mid latitudes in the summer, especially late afternoon. Like I said, those are the late summer, like isolated thunderstorms. Where severe thunderstorms, they form those mid latitude frontal collisions along the jet stream. They form along this jet stream in the mid latitudes. Or those air mass thunderstorms, they form all the time in the tropics and in the summer in the mid latitudes. So a single cell is not moving, that's why it cuts itself off. Where a severe thunderstorm, it's moving with the front, and so it's always moving, and so the downdrafts never shut off the supply of warm, moist air. So it can increase in intensity. So here's a map of thunderstorm occurrence in North America. Basically, these are the number of days in which there are thunderstorms in the country. And you can see the most thunderstorms occur in Florida, right? We have over 100 days of thunderstorms in Florida, and 80 to 99 in this blue area, 60 to 79 days of thunderstorms in the purple, and so forth. So it's the southeastern United States. Why is this? Because the warm, moist air necessary for thunderstorms, so we need that moist air because we need that, it needs to be warm because it wants to have to rise up through the atmosphere. It needs to be moist because that's the source of energy. The latent heat of vaporization in the water vapor. Well, that comes from the Gulf of Mexico. So that's the source of this warm, moist air. And so it's here that the warm, moist air then collides with cooler, drier air from over land, and it forms a front and generates these thunderstorms. So this warm, moist air moves inland. It then rises up through the cooler, drier air, and then causes a thunderstorm. So thunderstorms can wreak havoc through their heavy rains, flash floods, hail, high wind speeds, either straight line winds or tornadoes, and lightning caused deaths and fires. So heavy rains and flash floods, thunderstorms can be a major supplier of water to an area, and what happens is if the ground can absorb a certain amount of water, but if it keeps on raining, the ground becomes saturated and the water can no longer soak into the ground, and so it's just forced to run off, and that's how you get flash floods. That's how you get flooding. Then there's hail. Hail can be destructive, especially if there are larger pieces of hail. The stronger the updrafts, the larger the pieces of hail become, and also we have the destructive winds. So hail are layered ice balls. They drop from storms with very buoyant hot air rising from the heated ground. The upper level air is cold, which creates a large temperature contrast, and strong updrafts keep the hailstones aloft while adding layers. And the stronger the updraft means the larger the hailstone can become before the gravity of the hailstone overcomes the upward force of the updraft. So the stronger the updraft, the longer the ball of ice becomes before it falls. And there's been reports of baseball, even close to softball size hail in some portions of the country. So hail is most common in late spring and summer along the jet stream in the colder mid-continent region. So this is the number of major hailstorms from 1955 to 67, giving you an idea of the frequency of hailstorms. So Oklahoma has the largest number of hailstorms. It's centered around there. So Texas, Oklahoma, and then this is Kansas, parts of Nebraska and Missouri. So the destructive winds of a thunderstorm, we have both the straight line winds and damaging tornadoes. And then we have the widespread powerful windstorm that's called a derecho. Derechos are advancing thunderstorms. They form a line of ferocious winds. They have hurricane force gusts lasting to 10 to 15 minutes. For example, there's an Ontario to New York derecho in 1995, a thunderstorm moving 80 mile per hour with 106 mile per hour gusts. It blew from Ontario to New York for 2 hours in the early morning. So this storm was fueled by hot, humid air being supplied to the thunderstorm throughout the night. So just very long, sustained, high-speed, straight-line winds. Those are these derechos. It can be very damaging. They approach hurricane force winds. Then we have tornadoes. Most of us are familiar with tornadoes. They're rapidly rotating columns of air that form from large thunderstorms. They have the highest wind speeds of any weather phenomenon. They're more intense and more localized than hurricanes. About 70% of Earth's tornadoes occur in the Great Plains of the central U.S., and they move from the southwest to the northeast. That's the direction of the westerly winds, and they track along the jet stream as well. The jet stream usually trends in that direction. They travel up to 100 kilometers per hour with winds and have wind speeds up to 500 kilometers per hour. The core of the vortex is usually less than 1 kilometer wide, and it sucks up objects. And from hundreds of meters high in the atmosphere, they form hundreds of meters high in the atmosphere, and tornadoes may never actually touch the ground. So how tornadoes form is you need wind shear. You need wind blowing in different directions at different altitudes. So basically you need 3 air masses. Along the ground, you need warm, humid Gulf of Mexico air. And at mid-altitude, you need cold, dry air that's coming down from the Canadian, the Rockies. And then at the highest altitude, you need the jet stream moving. So you have the warm, humid air moving to the north from the Gulf. Then you have the air at mid-altitude, the cold, dry air moving, maybe to the south from Canada. And then at higher altitude, you have the fast-moving air of the jet stream moving to the east. And this creates wind shear. So as the warm, moist air from the Gulf moves up through the atmosphere because it's lower density, these different air masses at different altitudes moving in different directions cause the air to rotate. So the rising Gulf air is spun one way by the mid-altitude cold air and then spun another way by the jet stream. It's creating a corkscrew effect. So the warm air rising on the leading side, and there's cold air descending on the trailing side. And so you can see how this creates, you have air moving in one way, air moving another way, and then as it uplifts, it creates this corkscrew effect. The air starts to rotate. So we need this wind shear. We need air moving in different directions at different altitudes to create these tornadoes. There's a picture of a tornado there. So thunderclouds are tilted by the wind shear and may grow into supercell thunderstorms. So supercell thunderstorms are just very large frontal cyclones. The rain falls with the downdrafts in the forward part or the forward flank of the storm. And the warm air rises, that's the source of energy, the updrafts in the middle of the storm. And there's downdrafts of cool, drier air in the trailing side of the storm. And so the tornadoes, they form between the updraft and the rear downdraft. And so the rotation develops in the wind zone. So the core pulls into a tighter spiral. The speed increases dramatically. This is because angular momentum is preserved. So the tighter the spiral, the faster the wind speed, just like with a figure skater. As they pull their arms and legs in, they rotate faster. And as they spread their arms and legs out, they rotate slower. That's the conservation of angular momentum. So the tighter the core or the vortex, the faster the winds rotate. So the downward moving air in the center is surrounded by the upward spiraling funnel, and the wind speed is the highest a few hundred meters above the ground. So right near the ground, the wind speed is slowed down by friction. So the highest wind speeds are found a few hundred meters above the ground. So tornadoes in the United States. So air masses collide in the interior US, which is known as the world tornado capital, and they head northeast. So here you have average number of tornadoes per year per 10,000 square mile. So obviously, once again, Oklahoma is the most frequent occurrence of tornadoes. But you see, there's a kind of like a bullseye effect of frequency around that, and they tend to travel to the northeast. And you can see the number of tornadoes as a function of month. Number of tornadoes days with a tornado are yellow. Number of tornadoes are green. It peaks in basically spring and early summer. And why is that? Well, if you remember in the last lecture, it's the spring and early summer that the northern hemisphere begins to receive more energy from the sun, and so the land heats up faster than the water, and so the air over the land begins to rise, and that as a result it pulls in air. And the most important part is it's pulling in this air here. This air is now being pulled inland by the rising air over the land, and so there's warm, moist air from the Gulf. Yeah, it's not as warm as the air over the land, but still it's moist air being pulled inland from the Gulf. And whenever it mixes with these other air masses coming in, it creates these large thunderstorms from which the tornadoes spin off of. We use what's known as the enhanced Fujita scale to measure the size of a tornado. So the enhanced Fujita scale, it ranks on wind speed, where we used to use simply the Fujita scale, which was based off of incurred damage. However, that is more subjective in that a tornado of the same size, same wind speed, could cause different amounts of damage depending on the type of infrastructure present. So using the enhanced Fujita scale is more objective, where the size of the tornado is determined by its wind speed. So an EF0 tornado has 65 to 85 mile per hour winds, so siding and shingle damage. And then we have an EF1, EF2, EF3, and largest is an EF5, where there's incredible damage, deformation of mid and high-rise buildings, and there's wind speeds of over 200 mile per hour. So an EF5 is an extremely large and destructive tornado. Even EF4s are significant, and EF3s. EF2s can even take permanent houses off of their foundations. So there's three main destructive actions of tornadoes. So we have the high wind speeds, which are the most obvious. Then we have the wind-thrown debris. So the debris is picked up and thrown by the wind, and that debris can act like bullets or shrapnel, which is very hazardous. Then also the fast-blowing winds into a building rapidly, they increase the air pressure inside. What actually happens is the air pressure is decreased significantly outside, which creates a relatively large pressure difference between the inside and the outside. And sometimes that could blow out the windows or lift the roof. lift the roof slightly off of the structure. So there has been a declining number of tornado deaths in recent years. So there's more risk to older people, mobile home residents, and occupants of exterior rooms with windows, and those that are unaware of any alerts. You're safer in a car than a mobile home because a car has a lower center of gravity. It's less likely to be rolled. So this is the decade going up to 1920, 2009, and these are the recorded deaths. And you can see the number of deaths has been decreasing significantly. Part of this is improvement in infrastructure, and also a large part of it is improvement of early warnings. So, and more effective communication as far as warnings, so people can get out of harm's way. So we have the deadly dozen of states where tornado deaths. So from 1950 to 2010, these were the total deaths. So Texas ranks number 1, then Mississippi, and so forth. Where the deaths per capita, so this is the deaths per certain number of people, Mississippi ranks higher. So that means is there are more people that die in Texas, but relative to the number of people in the state, more people die in Mississippi, and Texas is actually not even on this list because there's so many people in Texas. So you have actually a higher chance of being killed by a tornado in Mississippi because a higher percentage of the people in Mississippi are killed than in Texas. So Mississippi is a very, right here, it's a very lethal state for tornadoes. And Arkansas, Kansas, and Alabama, Oklahoma. And so notice that these states happen to fall in what's called Tornado Alley. And also they have a lot of mobile homes. And mobile homes are terrible for tornadoes because they are easily rolled over and easily destroyed by tornadoes. So U.S. tornado fatalities by location from 1985 to 2008, you can see 46% of fatalities occurred in mobile homes, 26% in permanent homes, 10% in vehicles, 5% in school, church, 5% outdoors, 4% in businesses, and 4% are unknown. So obviously the most dangerous place to be during a tornado is in a mobile home. So some case histories, we had the tri-state tornado in March 1925, the largest known tornado. It moved about 100 kilometers per hour through Missouri, Illinois, and Indiana, leaving nearly 2-kilometer wide path of destruction. It destroyed 23 towns and killed 689 people on a 353-kilometer path. Then there was the super outbreak in early April 1974. There were 5 weather fronts. So we had the convergence of the cold front from the Rocky Mountains, a low pressure system moving east, strong polar jet stream. The bend to the south, there was warm, humid air from the Gulf of Mexico, the most necessary component, and then dry air from the southwest, overrunning the Gulf of Mexico air. So all the weather fronts came together as the Gulf of Mexico air burst up through them, through the inversion layer, which is the instability of density that created thunderclouds and set spinning by those thunderclouds were set spinning by the other converging air masses. In 16 hours, there was 147 tornadoes in 13 states, and 6 of those tornadoes were F5 force. So at that time, they still used the Fujita scale, not the enhanced Fujita scale. It was overwhelming destruction. You can see all those tornado paths during those 2 days on this map. So 10 out of 3,600 tornadoes between 1997 and 2000 have struck cities, including Nashville, Salt Lake City, Fort Worth, Oklahoma City. So there's been no direct hit of a very large tornado on a major city. Well, I guess you have the closest, you have Oklahoma City, the outskirts of Oklahoma City, an F5 hit. In Birmingham, Alabama, an F5 hit. All right, but we have 33 and 42 deaths in those instances. So in rooms, in structures built in, Tornado Alley, we have what's called a safe room. So the traditional cellar is really rarely built in these modern homes. And so what they do is they build an interior closet or bathroom that's built with concrete walls and a steel roof and steel door, or sometimes even a concrete roof. And so this safe room is a room, it's either a closet or a bathroom that all the occupants of the house know to go to in the event of a tornado. And often, in a very large tornado, the whole entire house could be destroyed, and that room itself with the concrete walls and steel door could be the only thing left standing. So what to do during a tornado? So if you're in a building, go to a designated shelter such as a safe room, storm cellar, or a basement. If no shelters are nearby, go to a small interior room on the bottom floor. Put as many walls as possible between you and the outside. Stay away from windows and doors. Get under a heavy piece of furniture and put your arms over your head. Do not stay in a building with a large, expansive roof, such as an auditorium, cafeteria, mall, manufacturing plant, or gymnasium, because the chances of that roof might be lifted off. If you're in a car, truck, or mobile home, get out immediately and go to a storm shelter or sturdy building nearby. In an urban or congested area, do not try to outrun a tornado. If you're caught outside with no shelter, lie down in a nearby ditch or depression away from stream beds, power lines, and cover your head. So you don't need to be near power lines, because if they break, they could pose a threat. And also stream beds, precipitation from the storm elsewhere could cause flash flooding. So you don't want to be in a stream bed. Do not get under an overpass or bridge in case it collapses, and watch out for flying debris. Now we're going to discuss lightning. So lightning is a leading cause of forest fires, and it's a major cause of weather-related deaths. So lightning distribution is the same as thunderstorm distribution, which makes sense. And so this map shows us lightning deaths from 1959 to 2009. So you can see the largest number of lightning deaths was 461 during this time period in Florida. You see Rhode Island had 6. It's one of the fewest, if not the fewest, based on this map. This is the map of global lightning strikes. So you can see the southeastern portion of the United States has the highest concentration of lightning strikes. So how lightning works? Well, lightning is just a flow of electric current. So the top cloud's excess positive charge, it seeks balance with the bottom cloud's excess negative charge. So there's a buildup of positive electrical charge in the top of the cloud and negative electrical charge at the bottom of the cloud. And that can discharge. And so the flow of electricity creates a bolt of lightning. And so that's the lightning you see that's up in the sky within the clouds. It speeds up to 6,000 miles per second in several strokes within a few seconds. This charge imbalance is neutralized. The charge imbalance is caused by the freezing and shattering of supercooled water droplets. So this causes a charge separation. And then those charges are distributed by updrafts and downdrafts during the early cloud buildup. The negative charge at the bottom of the clouds induces a buildup of positive charge in the ground. So you can see negative charge at the bottom of the clouds causes a buildup of positive charge in the ground. And so if the charge imbalance becomes large enough, then discharge begins. It begins within the cloud, initiates downward. There's a stream of electrons. It's known as a stepped leader. As the stepped leader nears the ground's electric field increases greatly, sending a streamer of positive sparks upward, connecting with the stepped leader about 50 meters above the ground. So what that's saying is the lightning bolt begins from the cloud as it's coming down. As it nears the ground, the lightning bolt another lightning bolt initiates from the ground, and it meets with the stepped leader about 50 meters above the ground. All right, so the connection of the stepped leader and the upward streams completes the circuit, initiates a return stroke of the positive charge of the cloud. So the more lightning strikes occur, temperatures of lightning are up to 55,000 degrees Fahrenheit. So don't get struck. Lightning can strike up to 16 kilometers from the thundercloud. So basically, there is a risk of lightning in any area in which the thunder can be heard. So in order to avoid lightning, get inside a house, don't touch anything. Lightning can travel through the plumbing, electrical, or telephone wires. Get inside, do not touch anything. Lightning usually flows along outside metal surfaces of a vehicle. It jumps to the ground through the air. Sorry, get inside a car, not get inside. So get inside a car, it'll flow around the frame of the car and jump into the ground. And if you're outside, move to a low place, away from anything tall, assume lightning crouch, and balls your feet with your hands over your ears. So it's all about reducing the conductivity. And so the more conductive your body is, the more electricity will flow through you. So if you get up on the balls of your feet, you have less of you is in contact with the ground, and it decreases your conductivity. So even if you would be struck by lightning, hopefully not as much electricity would pass through you, because what kills you is the amperage, the amount of electricity that actually passes through you. So that brings us to heat. So heat waves are invisible silent killers. Heat waves have been the biggest, as we see killers, as we have seen killers of all severe weather in the United States for the past 30 years. And the problems with heat are especially extreme in cities due to the phenomenon known as the urban heat island. So for example, in mid-July 1995, Chicago had a heat wave. And so here were the daily highs. There's the daily lows, and this is the normal high, was 84 degrees. So on July 14th, the low was almost equal to what the normal high was. You can see where we're almost 20 degrees above the normal high for that time of year in Chicago. So here's the heat index also plotted. And then the green bars are the number of deaths each day. So here's the peak of the heat, as you can see, but the number of deaths, it trailed the peak heat. And why is that? It's because heat doesn't kill instantly. Heat it taxes the body, because the body does not work optimally at high temperatures. So older people, elderly people, and babies, less than a year old, they have a harder time regulating their body temperature. And so if they're exposed to large amounts of heat, their bodies become taxed, more and more taxed, and they die of either heat stroke or heat exhaustion. And so the urban heat island, this is a phenomenon where dark surfaces such as concrete or asphalt, they heat up very quickly because they have a very low specific heat, as opposed to green spaces with vegetation or water. So in urban regions where there's a lot of asphalt and concrete, they heat up very quickly. And also the concentration of tall buildings reduces the amount of airflow. So there's not as much airflow to remove the heat. So there's a buildup or excess of heat in these urban regions, and that's called the urban heat island. And so the largest risk of death due to heat is usually in urban regions. In particular, it's in apartment buildings and higher floors, because the higher you go, the more heat accumulates. It's also elderly people, because sometimes they might be they're not as mobile, and they can't leave their apartment to find a cooling center, and they might not have family or someone checking in on them. And so they can unfortunately perish in their apartment if no one is paying attention to them. So that's why it's important that the local, police and fire departments, they do wellness checks on elderly populations in the region during heat waves. So that concludes our lecture on severe weather. Thank you very much.